So what is the value of the pivot position in column 3 of that augmented matrix? 5. That's column 3. Pivot position of that row is a 5. Does that matrix that I wrote down there represent a consistent system? Nope, because this says 0x plus 0y plus 0z equals -4. And it's impossible to have 0 equal -4. So not consistent means that there are no solutions. Did you read the syllabus? Yes. Good. Okay, so to remind you how the quiz grading works, you get a maximum of 4 points. 1 point for writing your question on a note card. Okay. 1 point for each question you got right on the quiz. And then you can get 1 more point if you got a quiz question wrong. You can replace that point if you took notes on the reading. So maximum of 4 points. So whatever you have, write that down on your folder, which I forgot to hand out, next to today's date. All right, so we'll do exercise 1. Prove that the sum of an odd integer and an even integer is odd. So first thing I'm going to do is try to write this as an if-then statement, because that's sort of the template I use for a proof. It has to be an if-then form. Okay, so I want to say if you add an odd integer and an even integer, then this theorem says that the result should be odd, right? Then the sum should be odd. All right, so I have it in if-then form. Let's just check a few. Make sure that you believe this statement before you start putting a lot of effort into trying to prove it. So an odd plus an even. 3 plus 2 is 5. That's odd. Yeah. Another odd plus an even. 7 plus 8 is 15. That's odd. Okay, I believe it, right? So the way proofs work is you start by assuming the if part. You assume that that if part is true. So I'm going to assume we have an odd integer and an even integer. Assume n is an even integer and m is an odd integer. So I assume that I have an even and an odd, and I'm going to add them together, right? But before I add them together, I'm going to apply the definitions of even and odd. So thus, n equals, we talked about the definition of even together last class, and we said a number is even if you can write it as 2 times something, 2 times another integer. So we're going to say thus n is 2 times something, where k is just some element of the integers. Okay. So what do you think the definition of odd should be? Yeah. Yeah, either one is fine. The convention is +1, but you can use either one. 2 times something plus 1 is how you get an odd number. So we're going to say the definition of an odd is that it can be written as 2 times something plus 1. It's not necessarily the same something that we're used for the even, right? So because we're not adding 2 and 3 or 4 and 5 or 10 and 11, right? Because it's not necessarily consecutive even and odd. So it's not necessarily the same 2 times something. So we'll call it something else. M is going to be 2j plus 1 for some j, an element of the integers. So we assume that we have an even and an odd integer. We apply the definition to even and odd. Now we're going to see what happens when we add them together and try to prove that whatever we get when we add them is odd. Now we see that n plus m, the sum of my even and my odd, just do a little substitution here. So I've got 2k plus 2j plus 1. So n was 2k, m was 2j plus 1. I'd like this to be able to write this as 2 times something plus 1, because that's the definition of odd. So I want to see if I can write this as 2 times something plus 1. So I'm just going to sort of key in on these two together. If I factor a 2 out of that, I have 2 times k plus j, and then I still have the 1, right? But k plus j is just an integer plus an integer, which is another integer, right? So this is 2 times an integer plus 1. So that means n plus m, the sum n plus m, now meets the definition of odd. Okay. So by the definition of odd, n plus m is odd. And once you prove it, do the little box with a check mark. Done. All right, so today we're going to refine and extend the methods that we learned last class. Last class, we just had a very brief introduction to the row reduction algorithm. So we used 3 elementary row operations to put a matrix in triangular form. And triangular form meant there was like a triangle of zeros in the lower left underneath the diagonals. Okay, so to make that happen, we worked column by column from left to right. And you use the nth row to eliminate all entries in the nth column below it, below the nth row. So a matrix in that form, we were calling it triangular, and that was sort of pretty colloquial language, but we can also, it's more technically referred to as echelon form. So it turns out that what we learned last class, while sufficient to solve the system, because you end up knowing what z equals, and then you back substitute to get y, and then you back substitute to get x. It turns out that's only half of a complete algorithm called Gaussian elimination. Gaussian because it was invented by Gauss, like the most famous mathematician ever. So what we did is we learned the forward phase of the algorithm. Half of it, the forward phase. Forward meaning work column by column, left to right. Today we're going to learn the backward phase, where then you work backwards, column by column, right to left. Okay? So you do the forward phase, and then after that, our goal is to get rid of everything above the diagonal. So you're only going to have entries on the diagonals, and then you'll know the solutions to the whole thing. You no need to back substitute. When you're done, we call that matrix reduced echelon form or reduced row echelon form, abbreviated RREF. So to obtain it, you work column by column, right to left. Okay. So we're going to do one together, and then maybe we'll do even another one together. Make sure everybody can do this algorithm before I let you try it on your own. All right, so first thing I'm going to do here is translate this to an augmented matrix. So augmented means you have the coefficients, then a vertical line, and then the constants after the equal sign. So I have 2, 0, 3. Those are my x coefficients. My y coefficients in my system are 0, 1, 6. And my z coefficients are -6 to -2. Put a vertical line to represent the equal sign. Your textbook does not do this, but it's so common that I kept it because so many people use Khan Academy and stuff, and they use the vertical line. Then you put the constants on the other side. So -8, 3, -4. Okay, so I'm going to do the forward phase, the part that we learned last class. So my first goal is to have a 1 in the upper left. So I could scale that whole row, right? Just I could divide that whole row by 2, multiply it by 1/2, same thing, right? So row 1 is going to become 1/2 row 1. That's my first step. So I have 1, 0, -3, -4. And then the other 2 rows stay exactly the same. 0, 1, 2, 3, 3, 6, -2, -4. Done. Okay, so I have a 1 in my upper left. My next goal is to have all zeros beneath it. There's already a 0 in the second spot, so I can leave that alone. I need to make that 3 in the lower left a 0. So I need to change row 3. So my next step is that row 3 is going to become something new, okay, because row 3 is what needs to change. The way you change a row is you can add itself to a multiple of another row. So row 3 is going to be row 3 plus a multiple of another row, and the row I'm going to use is row 1, right? Because it's got this nice handy 1 in it that I can multiply by anything I want. So what should I multiply row 1 by so that when I add it to row 3, I cancel? -3. Now, it can be really handy when you're first starting to do this algorithm to write this out, right? Write out the step, row 3 plus -3, row 1. I'll do it in another color. Okay, so row 3 plus -3, row 1. Okay, so row 3 is 3, 6, -2, -4. -3 row 1 is going to be -3, 0, -6, -9. Add them, oops, and I get 0, 6, -8, -13. That's my new row 3. Nothing else changes. So it's a very common mistake to replace row 1 with this new thing that you wrote, but that's just part of the work. It's not part of the next step. Yes. Negative. Oh, yeah, I was looking at row 2. Thanks. Okay, you're right. I was multiplying by row 2. Let me fix that. Okay, -3 times row 1. So that should be -3, 0. -3 times -3 is 9. And -3 times -4 is 12. Did it right that time? Okay. So now I get 0, 6, 7, 8. Okay. Thank you. All right, so I go to my next matrix. Row 1 is exactly the same as it was. Row 2 is exactly the same as it was. Row 3 is the only thing that changes. It's getting replaced with what I just calculated up there. So I have 1, 0, -3, -4, 0, 1, 2, 3. And then my new row 3 is 0, 6, 7, 8. All right, so column 1 is done. It's got a 1 in the top entry, zeros beneath it. Move over a column, and you want, in the second column, you want the second row to have a 1. Okay, so that's done. It's already a 1. If it weren't a 1, you just scale the row, make it a 1. Then you want zeros below it. Okay, so I want that 6 to be a 0. I don't care yet what's above it. Just want underneath it to be a 0. So I'm going to make that 6 into a 0 by changing row 3, right? So row 3 is going to become row 3 plus a multiple of another row. Which row do you want to use? 2. Yeah, because it's got the 1. That's why we want that 1 there, so we can use it to knock out everything below it. So I'll do -6 row 2. All right, I'm going to do this one without writing down the side work. So 1 and 2 stay the same, so I can do those real fast. Okay, so row 3 is changing. It's going to be itself plus -6 row 2. So 0 plus -6 times 0 is still 0. That's good. If you changed that number, your step is the wrong step to take because you don't want to mess up the work you already did to put those zeros there. Okay, 6 plus -6 times 1 is 0. 7 plus -6 times 2, so that's 7 plus -12 should be -5. And then 8 plus -6 times 3, which is -18, so that's -10. Drop a row, go over a entry. So I have ones on my, almost have all ones on my diagonal. I need this very last spot, that -5, I want it to be a 1. I can just scale that whole row to make it a 1. So row 3 is going to become -1/5 row 3. Okay, last class, this is where we stopped. This is sufficient to get a solution to the system. 2. Yeah. This says z equals 2, right? And then y plus 2z equals 3, and then x minus 3z equals -4. So you can back, as long as you know z, now we can back substitute to get y and x. So this is where we stopped last class. But we're going to keep going and finish solving using the backwards phase. Yes. Yep. This is echelon or triangular form. All right, I'm going to go to a new slide here and copy my matrix. 1 0 0 0 1 0 -3 2 1 -4 3 2. All right, so now I'm going to do the backwards phase where I'm going to now work right to left. So before I did column by column, left to right, I wanted to put the diagonal entries called pivots. I wanted to make them all 1s, use those 1s to knock out everything beneath it. Didn't care about what was above. Now I'm going to go right to left and use those 1s to knock out everything above it so that I'll only have 1s on the diagonal, 0s everywhere else. Okay, so I'm going to start with the third column and I'm going to knock out this 2. Okay, so I have 2 things I need to turn into 0s, so I'm going to do 2 separate steps here. First, I'm going to work on this 2. I would like that to be a 0. So it's row 2 that needs to change. So row 2 is going to become row 2 plus a multiple of another row, and I'm using row 3. Right? And the reason I want to use row 3 is because I have this nice 1, right? Because so it's easy to take a multiple of it. And I have the zeros over here, so no matter what I multiply by, I'm not going to mess up anything I've already done. So I'm going to do -2, row 3. So my new matrix, 1 and 3 don't change, so I have 1, 0, -3, -4, and 0, 0, 1, 2. Rows 1 and 3 don't change at all. Row 2 is the only one that's getting updated. And if I do -2, row 3, so -2 times 0 plus 0 is still 0. -2 times 0 plus 1 is still 1. So that's nice because I already did work to get that to be a 0 and that to be a 1. I don't want to mess up that work I already did. And then -2 times 1 plus 2 is now a 0. And -2 times 2 is -4 plus 3 is -1. All right, so my next step is I want to get rid of, I want that -3 to be a 0. So that's in row 1. I need row 1 to change. So row 1 is going to become itself plus a multiple of another row. And again, I'm going to use row 3 because it's got the 1 to help me. So it's going to be 3, row 3. Row 1's the only one that's changing, so I usually start by copying the things that don't change so I don't mess them up. Okay, so row 1 is going to become itself plus 3, row 3. So 3 times 0 plus 1 is still 1. 3 times 0 plus 0 is still 0. 3 times 1 plus -3 is 0. 3 times 2 plus -4 is 2. So that is the third column. I managed to get zeros all above the pivot. Next, I would move to the middle column and make sure I have zeros above the 1, but that already happens to be a 0, so I'm done. So now I can translate this to equations. This says x equals 2, y equals -1, z equals 2. Any questions? No, not at all. No. Just variable names. All right. Should we do one more together? Or do you think you got it?
Good question.
Sure.
Always going to be starting on a right with working backwards?
Yes. Yes. So yeah, when you do the forward phase, you always start in the top left, knock out everything below it, and then move down diagonally. And then when you go backwards, you start with the bottom right, knock out everything above it, and then move right to left, moving up. Knock out everything above your pivots. So this is the prettiest that it can come out, right? When your coefficient matrix just has zeros and ones in it, right? That's like sort of like my favorite. But sometimes if you have more equations than variables or more variables than equations, you will have spots in your matrix that aren't ones or zeros. Okay? So don't be surprised by that. It's not that this is always going to be the result. This only happens when you have the same number of equations as variables, and there is one perfect solution. Only one set of numbers that will make those all true at the same time. So in the next example, as part of your group activities, here you have only 2 equations with 3 unknowns. Okay, so we could see what happens when we row reduce this. So I'll do the row reducing with you, and then I'll let you answer all the questions about it in your groups. All right, so to set up an augmented matrix, So I need the x variables, so that would be 0, 1. Y variables, 1, -3. Z variables, -2, 4. Augment with the constants, 3, -6. And then I want to use row operations to put this matrix into reduced echelon form. So my first goal, I'm going to work column by column, left to right. And my first goal is to have a 1 in the upper left. Easiest way to achieve that is to just swap those two rows. Okay, so I'm just going to do 1, -3, 4, -6, and 0, 1, -2, 3. All right, so now my whole first column is done. I have a 1 in the upper left, all zeros below it. Move to your next column. You want to have a 1 as its leading entry. Already done, right? But then there's no more diagonal entries, so there's nothing else that I need to turn into 1s, right? I'm going down 1 over 1, and then the next pivot position would be in the next row, further to the right than the 1, but there is no next row. So these are my only 2 pivot positions. So I have nothing else that I need to turn into 1s. I've gone as far to the right as I can, getting pivots and putting zeros beneath them. So now I'm done with the forward phase. That's as far as I can go. So then I would work in the backwards phase, and there is no pivot in this column, so there's nothing I can do to that one. You start with your first pivot position, right? So in our previous example, it was the last column, but you want the last pivot, okay, which is your first non-zero entry of each row. So I have a 1 here, I want to make a 0 above it. So my next step is going to change row 1, is going to be row 1 plus 3 row 2. So row 2 stays the same, 0, 1, -2, 3. Row 1 is 3 plus row 2, or row 1 plus 3 row 2. Okay, so 3 times 0 plus 1 is still 1. 3 times 1 plus -3 is 0. 3 times -2 is -6, plus 4 is -2. And 3 times 3 is 9, plus -6 is 3. That is the best we can do, right? So we worked left to right, making the leading entry of each row a 1, with zeros above and below it. So that's reduced row echelon form. Each row, the first non-zero entry is a 1, and there are zeros above and below it. That's the definition. Then there's other stuff, right? There's other stuff that's not as pretty and satisfying as having a square matrix with all 1s and 0s. So what I do with this is I'm going to have you circle the pivots. There's a pivot and there's a pivot. Those are the leading entries of each row. The first non-zero entry in each row is called a pivot. So the variables that correspond to pivot positions are called basic variables. So remember that this column was originally set up as the x coefficients. The next column was the y coefficients, then the z coefficients, then the constants. So columns, the variables that correspond to pivot positions are called basic variables. So this would be an x and a y. So x and y are basic variables, because the pivots are in the x and the y column. And any variables that don't have a pivot position are called free variables. So the z column has no pivot position in it, so we call that a free variable. All right, so I'm going to translate that last matrix into equations. This says x minus 2z equals 3. right? And then the next column said y minus 2z also equals 3. So what happens is that I actually have an infinite number of solutions, right? There is no single x, y, and z that makes that system true. There's an infinite number of solutions. So to write down the general solution, you solve for each basic variable in terms of the free variables. So if I look at x minus 2z equals 3, x is a basic, z is free, solve for the x. So this just would be x is 2z plus 3. In the next equation, you have y is a basic, z is free, solve for the y. So y is also 2z plus 3. And then z is free. So that's just a convention of how you write down the general solution. And to give two specific solutions, I'm going to find two specific x, y's, and z's, two sets of x, y's, and z's that solves the system. So pick any value for z. Pick a real easy value like 0. Yeah. If z is 0, then y is 2 times 0 plus 3, which is 3. And x is 2 times 0 plus 3, which is 3. So there's one specific solution. If you make x, y, and z 3, 3, and 0, you solve the system. And there are infinite solutions. We could come up with another one by picking a different z, right? If I make z 2, then y is 2 times 2 is 4 plus 3 is 7. And x is 2 times 2 is 4 plus 3 is 7. There's another solution. All right. I think what needs to happen is you need to just like grapple with some problems, and I'll come around and help you. Start with number 2.